Chapter 15, The Data Asset, Databases, Business Intelligence, Analytics, Big Data, and Competitive Advantage. Business intelligence consists of the various methods and tools used by enterprises to manage the data used to make business decisions. These tools start with a database used for storing gathered information. The database is made up of tables tied together by logical relationships. Database management systems are used to manage these complex data structures. At a higher level, multiple databases may be integrated into shared data warehouses and data marts. These integrated systems are used by management to extract and share information based upon complex business models and queries. Why do we gather all of this data and create complex data models and systems? Business intelligence is the application of these technologies in the gathering and analysis of the data. The goal is to transform the data into information which may be used to make key business decisions. The central point of data storage is the database. A database is a collection of records or pieces of information and is made up of the actual data and related information. The data schema is a structural description of the database, including definitions of the facts captured, the various logical objects within the database, and the relationship between these objects. A database is a collection of records managed to ensure integrity and quality. The database facilitates controlled access to the data and supports the schema, which defines the structure of the data. The database includes a query language like SQL that enables users to extract data from the database according to complex algorithms. The database holds information about the included objects, events, people, and places. The information is structured into models that are commonly hierarchical, network, or relational. The hierarchical model uses a tree-like structure. One object can link to multiple objects through a parent-to-child relationship. One object is the parent to multiple children. For example, a one-to-many relationship exists between NIU classes and students. One class has many students. This structure can limit the possible links. The network model uses a flexible lattice structure, which offers more variability and has the ability to depict more real-world combinations. Here we can have multiple parents with multiple children, resulting in many-to-many relationships between objects. The result is a set of mesh relationships. The third model is relational and contains multiple logically related two-dimensional tables. Relations are usually one-to-one, one-to-many, and many-to-one. In this depiction, the one-to-many relationships between tables of data are shown with arrows marked with a number 1 and an infinity symbol to indicate the many side of the relationship. We see in this diagram that one customer can have many orders, and that the orders are linked to the customer by the customer ID field. The latest data model is post-relational and is organically related with multi-dimensional tables, offering a higher level of flexibility, and as a result can model increasingly complex data. The database structure includes entities, which are persons, places, things, transactions, or events. Each entity generally fills one row in a table. For each activity, attributes are captured, which are the characteristics or properties of an entity. These attributes fill the fields or columns in a table. Similar entities can be grouped into entity classes. Entity classes offer the opportunity to reuse schemas and related queries. They are stored in a two-dimensional table within the database. While not a full database management system, Microsoft Excel can perform many database functions on its own. Here we see an example of a simple entity attribute structure. Notice that multiple attributes may be associated with each entity. In this case, each entity is a different student. For each student, we have attributes showing the student's ID, name, and phone number. This example shows how many data tables are structured. Each table will have at least one primary key. The primary key uniquely identifies each entity in a table. No two entities have the same primary key. For example, at NIU, each student is uniquely identified by their ZID. Every student has one, and no two students have the same ZID. Other examples include Social Security number, customer number, order number, and part number. This is important to guarantee the integrity of the data. The primary key ensures that the data associated with a given entity is accurate and prevents confusion. For example, without the ZID, you would not be able to differentiate two students with the same first and last name. More complex relationships can be established within the data with compound, combination, or composite keys that have the ability to group multiple fields together. Tables are linked together through the combination of a primary key and a foreign key. The foreign key is when the primary key from one table appears as an attribute field in another table. For example, customer ID is the primary key in the customers table, and customer ID acts as the foreign key in the order table. Similarly, in the orders table, order ID is the primary key that acts as the foreign key in the order details table. We can also see that the order details table has an additional foreign key, product ID, which creates a link to another table not shown here. These relationships give the database tools the ability to organize data logically. The user can answer questions like what orders did a particular customer place. You would start with the customer name in the customers table and find the associated customer ID. Then we use that customer ID to find the associated orders in the orders table. This is just a simple example. Much more complex queries are possible. Relational databases provide increased flexibility since one physical implementation can have multiple logical views. The user can create any number of logical structures and queries based on one set of data tables. Relational databases have scalability. We can add entity classes, tables, and other elements as needed. Database administrators can use various tools to optimize performance around key queries and reports. In older data stores, repeating data was a problem. Imagine receiving a customer order that has the ship to information included. Luckily, you receive an additional order with a similar but different address. Is this the same location with a typo, or is it truly a different address? Manual intervention would be required to straighten this out. With relational databases, however, this problem is resolved as there is only one copy of the address in the database, which is then linked to each subsequent order received. Individual entity classes can be kept clean by recording data only once. Security can be enforced on a more granular level, with only selected employees having the ability to change data within customer records. For other employees, read-only access can be granted for viewing the data without the ability to make updates. It is essential that large databases have accurate data within them. Automated systems can generate mass quantities of errors if they are using incorrect data. Relational databases provide increased information integrity and quality. One technique includes the use of relational integrity constraints. Rules can be established to control updates. In addition to only giving some users write access, the database can be configured to check the data being entered. For example, users would not be allowed to enter letters when numbers are expected, with pricing, for example. We could also block orders coming in from customers not already in the database. In this case, the order would be rerouted to have the new customer information loaded first, and then the new order. There may be other business-critical integrity constraints like not allowing orders for customers over predefined credit limits, or not accepting orders from customers who are past due in their payments. Database management systems, or DBMS, come in many forms. DBMSs are often based upon a software program like Microsoft Access or DB2 from IBM. More advanced systems can be integrated with the tools necessary to run the entire enterprise. Enterprise Resource Planning Tools, or ERP, are often used by larger multinational organizations. Two of the most popular ERPs are Oracle and SAP. The ERP market share data for 2018 is shown here. There are two types of logical structures that are typically used. With direct interaction, the user sends a request to the DBMS, and the DBMS interacts directly with the actual database. With indirect interaction, the user interacts with a separate application like an accounting system, which then interacts with the database management system. The IT architecture used when implementing a database management system can vary based on need. In this example, we see a design where users access the data by way of a web interface. Valid requests travel through the corporate firewall to a web server. The web server interacts with business applications like accounting or order management. These applications can send and receive data from the database by linking to the SQL database. This is an example of an indirect interaction. Most major enterprises use multiple databases. This may be due to different business needs, different applications, or the evolution of business systems over time. To keep these databases in sync, tools exist that integrate information among multiple databases. Forward integration occurs when information entered into one system flows downstream into all others. An example might be when the sales team updates a customer address in one system, which is then copied to related tables in all company databases. With backward integration, information entered into one system flows upstream into all others. An organization could use one method or both. This would depend upon the database structure and where the organization wants key data to be controlled. We may grant write capability to select employees to minimize errors and duplicate entries. A data warehouse is a central repository of integrated data from different sources within the business. It is established to collect key data for reporting and analysis. The data warehouse holds a select subset of the enterprise data. This data is then used to generate management reports to guide in the decision-making process. Gathering this data in one location simplifies the creation of management reports, eliminates duplicate data, and speeds report outputs. The data stored in the warehouse is uploaded from the operational systems, such as marketing or sales. The data may pass through an operational data store and may require data cleansing for additional operations to ensure data quality before it is used in the data warehouse for reporting. The data mart is a view into a data warehouse used to retrieve client-facing data. The data mart is a subset of the data warehouse and is usually oriented to a specific business line or team. Since the data is available to a specific client, the interface may be customized to specific requirements. The data warehouse pulls data from a number of operational information systems, including accounting, order entry, and customer service and sales. These systems typically contain silos of information that may have inconsistent formats and structures. By pulling this data into the data warehouse, we can select only relevant information from these systems. We can also take data from the data warehouse and forward it to the operational systems as appropriate. The data warehouse can include both current and historical data. It can also be used to store projected data to be used for business forecasts. Many operational systems are not designed for analysis and decision support. Even if they are, their methods will vary. The data warehouse can present one clean set of data with a common interface to users. Another justification for the implementation of a data warehouse is based upon the issues found with operational information systems. The flow of information in and out of operational systems may be slow. Plus, we don't want to slow down operational systems and thus our operations when we run our reports. Relevant information may be difficult to find within the operational systems. Most operational systems are real-time and retain a limited amount of historical data. As a result, analysis of past activities may be difficult. Remember the goals of data warehousing. Ultimately, the data warehouse is designed to support the business decision process in a timely manner. We need a source of data to understand the past and plan for the future. The data warehouse can also provide a feedback loop into data selection, ensuring data integrity and providing quick feedback in the case of errors or inconsistencies. A data warehouse is a logical collection of information supporting business analysis activities and holds a clean subset of all the data in the business. It is not just the sum of the individual databases. The data warehouse is designed to assist with decision making in support of the organization's primary mission. The data warehouse collects and stores a set of integrated data from multiple operational systems. Data is transformed into information which is then used for decision making. This integrated data repository helps the company forecast the future, identify trends, and most importantly, make key business decisions. The data warehouse aggregates information from different applications and locations throughout the organization into a single repository to enable business analysis and decision making. This capability supports the overall success of the enterprise. The data warehouse is created by pulling transactional data from appropriate internal databases. Data may also be retrieved from external databases if necessary. The formal term to describe this process is extraction, transformation, and loading, or ETL. The ETL process starts by pulling from multiple sources, internal and external. Next, the data may be transformed if necessary, such as in the case when the data structure in the source database differs from that of the data warehouse. For example, various systems may store address information differently. Transformation does not change the data, but only changes the structure by comparing the enterprise data definitions. Finally, the cleansed data is loaded into the data warehouse. The last step is to send subsets of the data to the designated data marts. The data transformation process uses enterprise definitions to cleanse or scrub the data. The goal is to identify issues and then fix or discard bad data. Bad data can be inconsistent, such as when the address for a company is different in two different databases, incorrect, or incomplete. Data cleansing is necessary to prevent errors in the business. For example, if two records exist for the same customer, we might accept a second order for a product while the customer is delinquent paying for the first order. The data warehouse is different than the data mart. The data warehouse has an organizational focus, while data marts have business or operational unit focus. Data marts typically have a more specific purpose and might be focused on manufacturing, production, sales, or finance. Data marts are designed to provide the user the right information quickly. The other major purpose of gathering business data is to enable business analytics. Data is used for statistical and quantitative analysis. The goal is to understand the various metrics used to manage the business and to predict future status. The ultimate goal is to support management in making the right decisions and planning for the future by using the facts and not just an opinion. The importance of the data available within the enterprise should not be underestimated. Your data provides a competitive advantage if it is not generally available and can be transformed into valuable business decisions. The benefits of all this data and number crunching are very real. Leveraging data lies at the center of competitive advantage. A number of companies are known for their operational data management skills. They take their operational data and use it to drive real-time decisions and long-term strategies. Netflix uses data analytics to collect data from their 151 million subscribers. They use this data to implement data analytics models to discover customer behavior and buying patterns. They use that information to recommend movies and TV shows based on their subscribers' preferences. Netflix earns over $1 billion in customer retention because the recommendation system accounts for over 80% of the content streamed on the platform. Netflix also leverages this data to conduct custom marketing, further driving their success. For Walmart, data mastery has helped vault them to the top of the Fortune 500 list. They rely on big data to get a real-time view of their workflow in the pharmacy, distribution centers, and throughout their stores and e-commerce platform. Walmart uses simulations at their pharmacies to understand customer demand, adjust staffing levels, and speed the customer experience. They use a similar approach to optimize the checkout process. Data analytics are also used to optimize their supply chain by tracking shipments, minimizing handling, and minimizing costs. They also use the data to provide customers with the best selection of products and enhancing the customer experience. By taking these steps, Walmart leverages their data to increase customer loyalty while minimizing operation costs. Data helped Harrah's Casino hotels grow to be twice as profitable as similarly sized Caesars. Harrah's grew to the point that they were able to acquire Caesar's Palace. Harrah's uses their data to drive customer loyalty. They track customer habits and deliver upon those needs. The casino delivers the recognition and service customers have come to expect. As a result, Harrah's has the most devoted customers in the casino industry. That loyalty resulted in strong growth and exceptional revenues. Companies use a number of approaches to entice customers to provide their data. Loyalty cards and reward cards can be used to track customer purchases. Also, discounts, cashback, and customer surveys are a great source of information regarding customer habits and preferences. The collected data is invaluable to the business. The primary issue evolves around the privacy of the customer. Privacy laws have been created to protect the personal information of customers. These laws vary by country and are particularly strict when it comes to financial and medical data. Data mining is the process of pulling useful data from the massive pools of data out there. Data mining can be used to establish customer segmentation by determining which customers are likely to be the most valuable to a firm. Another benefit is the targeting of marketing and promotion by identifying which customers are most likely to respond to which offers, at which price, at what time. Market basket analysis can also be performed to determine which products customers buy together and how an organization can use this information to cross-sell more products or services. You have probably seen the outcome of this process in use. When you consider a purchase, you might see a related product that others have purchased. The goal is to increase sales by focusing on interested customers. The fact that you went to the company's website in the first place is a good start. Other uses for data mining include collaborative filtering, where an individual customer's experience is customized based on the trends and preferences of similar customers. We may also look at customer churn to determine which customers are likely to leave. This data can also be used to prevent unwanted defections. Data mining is also used for fraud detection by uncovering patterns consistent with criminal activity. Data mining may be used for financial modeling by building trading systems to capitalize on historical trends. Finally, employee hiring and promotion can be augmented by data mining by finding characteristics consistent with employee success. Similar algorithms are used by Indeed to match applicants to job openings. Data mining had its start in artificial intelligence. The goal was to simulate the functions of the human brain. Next came neural networks, which are an artificial intelligence system that examines data and identifies patterns. Neural networks build data models to exploit these findings. The end goal is to use these data models to predict future trends and to leverage the marketplace. Expert systems are AI systems that leverage rules or examples to perform a task in a way that mimics human expertise. Generic algorithms are used to examine many potential solutions to a problem while varying different mathematical models. The variable outputs are compared to search for the best alternative. There are a number of commercial BI tools available. All offer standard canned reports used for repeated analysis of the data as it changes over time. In addition, custom ad hoc reporting is used to create unique reports as needed. Dashboards provide a quick view of critical information and are used by management to provide alerts to deviation in a given process. These alerts can be calls to action to change a business process or adapt to changing business conditions. Online Analytical Processing, or OLAP, looks for information that is not apparent in the data natively and can provide a more complex view of the data. These complex business intelligence tools are possible due to advances in technology, along with having a clear understanding of the meaning of the metrics gathered. These key performance indicators, if defined correctly, can be used to drive continuous process improvement and result in business success. This is the end of our discussion on the use of data to drive business success. Next, we will review social media and the sharing economy with a focus on Facebook.